let's look at some examples of friction in action, and hopefully it'll help you get around to what we've been trying to discuss. Okay? So here we have a nice simple example. We have an object on a horizontal surface, right, which is nice because then we know that the normal contact force is just going to be acting up, and the box is being pulled by a horizontal force of 8 newtons, right? And they want us to find the total contact force. Okay, so these objects are at rest. So if they are at rest, that means that the forces, the net resultant forces, must be in equilibrium. So my vertical components must be equal and my horizontal components must be equal, right? Right, so we want to find the total contact force. If we quickly jump back to over here, right, if we want to find the total contact force, you can see that I need to know the normal contact force, and I also need to know the friction force. So let's go and work those out, right? So I don't have, there we go. I don't have the normal contact force and I don't have the friction force. So those are the first things that I need to work out. So I need to work out what R is, right? So R is acting vertically, so I need to resolve vertically. And I can see the only other vertical force that I have is the weight of the object, right? Because these objects are at rest, that means they are in equilibrium. So R must be equal to the force acting in the opposite direction, and that's the weight. Okay? And we can see that that's just 5g because the object weighs 5 kilograms, and so R is equal to 50 newtons. Nice and easy one. So it's always nice when things are acting on horizontal surfaces because then we don't have to resolve or split up components to find the normal contact force. Okay, let's consider the friction force of this object. Okay. Again, this object is at rest, which means that my horizontal forces must also be in equilibrium. So the force of friction must be exactly the same as the force being applied on the object, right, which is 8 newtons. So there we have our two forces. Okay, we've solved for the contact force, the normal contact force, and we've solved for the friction force. Right, and now we want to find the total contact force. Right, so the total contact force is just the resultant force of these two forces. Because they happen at perpendicular angles, we can just use some Pythagoras. So if we remember the formula, right, see the total contact force is equal to the square root of the normal contact force plus the friction force, right, squared. Right? That's just from Pythagoras. And this is just a simple process of putting in the numbers. So we'll have 50 squared plus 8 squared. 8 squared, and we'll take the square root of the answer. And that's going to give us 50.6359. We go back to the beginning and we see what is the question. It doesn't say anything, so we'll have to go look on the front of the exam paper, and the exam paper will probably say 3 significant figures. And so this will be 50.6 newtons. A nice and easy one to start off the day. Cool. Everybody happy with that one? Okay, don't forget the basics. When something's not moving, that means the forces are in equilibrium, right? That means when we resolve, the forces perpendicular must be equal to each other. Okay, let's move on to a more tricky example. Okay, so let's ignore the diagram for a second. Let's read the question, and then you obviously would have to draw a diagram for yourself. In the textbook, they give it to you, right? It's not normally going to be given to you. You're going to have to draw one. So we have a book of mass 8 kilograms on a rough slope, which is at an angle of 20 degrees. So here we have our slope, and there's our 20 degrees. The book is held in limiting equilibrium by a force of 10 newtons up the line of the greatest slope. So the line of greatest slope means up the hill. Okay? Find the coefficient of friction and the magnitude of the contact force. So the magnitude of the contact force, that's going to be the total contact force. So once again, we don't know the resultant or the normal contact force, and we don't know the friction force at this point. Right, what we do know is that there's tension being applied up the hill or up the greatest slope of 10 newtons. And so this, Zara, is where we get into a conundrum. They don't tell us what type of limiting equilibrium this is. So I want you to imagine this book on the slope, and you are the person pulling the book up by 10 newtons. Does that mean that when we're pulling with 10 newtons, the book is on the verge of coming up the hill? In other words, the friction will be acting against us? Or does that mean that we're applying 10 newtons of force and it's just enough to keep the book from moving down the hill? Because if the book moves down the hill, the friction would be acting against it moving down the hill. So we don't know in which direction the friction force might be coming. And so we would have to make an assumption, right? And we might assume wrong, but our answer will tell us whether we've assumed correct or not, right? So I'm going to purposely, because I know what the direction is going to be, and I'm going to purposely assume wrong, right? I'm going to say that we're pulling this book with enough force to, I mean, it's only an 8 kilo, well, a book of that, an 8 kilogram book, my goodness me, okay? I'm going to assume that I have enough power to pull the 8 kilogram book up the hill, and I'm going to say then...
That is a very large book.
It is a very large book. I just read that now and thought, wow, okay. Okay, I'm going to...
It's almost as big as our physics book.
Yeah, I'm going to assume that I'm pulling this book up the hill. So I'm going to say this book is on the limit of coming up the hill, right? I'm pulling it up the hill. That means the friction is working against me, right? So it's against the direction of motion. The direction of motion I've indicated on the bottom here, right? I'm saying the book's going up the hill. And so the friction force is acting in the opposite direction to the force that I'm applying. So now we're going to solve for our contact force, our normal contact force, sorry, and our friction force. I know that the weight of this book is, holy moly, 18 newtons. Okay, the normal contact force is acting perpendicular to the surface of the slope, which means that it needs to be, we need to resolve it. Okay, so we're going to resolve perpendicular to that force. Instead of, because it's the unknown, remember when we have an unknown force, it's easier to resolve in relation to the unknown force rather than to what we normally consider vertical and horizontal. So in order to find the normal contact force, I need to find all the forces acting in the opposite direction. Remember, this object is at equilibrium. So the net force must be equal. So the only force that we can consider, right, this 10 newtons is perpendicular to that force, so it's not going to have an effect. Friction acts perpendicular to normal contact force, so it's not going to have an effect. But this 8 G newtons here, this is not acting parallel or perpendicular. So we're going to split that force up into its two different components. I'm going to split it off to the side here, right? You would do this on your actual diagram, but just because we don't want to make too much of a mess here. Right, so we're going to resolve these into its two different components, right? Using a little bit of triangle trickery here. This angle here is 70 degrees. And so if we had to draw a line down there, that angle down there is also 20 degrees. So we have 20 degrees over here. I'm after the vertical component. I'm after this component over here. Right? That is the adjacent side to that 20 degrees of this 8 g-newtons. So my normal contact force and this vertical component must be equal to each other, okay? Because this object is in equilibrium. And because the direction of motion is perpendicular to them, they will always be in equilibrium. So this is going to be 80 because 8g, that's going to be 80 newtons, right? It's the adjacent side, so this is going to be cos 20 degrees. $75.175, etc. Right now, I'm immediately going to store that into my calculator because we're going to have to use it later on. Right, there we have the normal contact force. Now we need to work out the friction force. Again, remembering that this object is in equilibrium, so the components must be equal to each other. So what are the horizontal components? Well, we have this friction component. We also have the horizontal component of this 8 newtons, which is this one over here. Right? We are assuming that these two forces are acting in the same direction. And then we have this 10 newtons over here acting in the opposite direction. Okay? So based on what we've assumed, we're saying that the friction force and this horizontal component here, this force here, that's the opposite side from 20 degrees. So it's going to be 80 sine 20 degrees. That must be equal to the force acting in the opposite direction. Again, because this object is in equilibrium. It's on limiting equilibrium. It's like just on the verge of moving, but it's not moving. And this is 10 newtons. So let's solve for the force. So I'm going to take 10 newtons and subtract 80 sine 20 degrees. And I'm going to get minus 17.3616. So here we have got a negative answer, right? So Zara, this is where you've now worked out that you've assumed that this force is acting against the direction of motion. You're assuming that the object was actually going to be moving up the hill, but you've actually got a negative number, okay? So this tells me that I've made the wrong assumption. The force is actually acting in the opposite direction to the assumption that I've made. If I had considered this force to be holding the object on the hill, in other words, this object was actually on the verge of slipping down the hill, that would have meant that this force here needed to actually act in the opposite direction. Right, so I'm going to redo my calculation, this calculation over here, except now I'm going to state that the force acting down the hill, that's the weight of the horizontal component of the weight. And I'm going to put my friction force on this side now, because I'm saying it's acting in that direction. All right, and if I solve for F this time, I will get 17.3616 newtons. So now I got a positive number. That means that the force is actually happening in the direction that I assumed. Does that make sense to all of you guys?
Yeah.
Yeah.
Yeah. So again, remembering that a minus sign doesn't always mean you've done something wrong. It just means you might have made an incorrect assumption. Right? If you're assuming the force must be positive and it's negative, well, it's just acting in the opposite direction to the direction that you assumed. So if you do make the wrong assumption, that doesn't mean you're going to get the answer wrong. But notice that the magnitude of both of these forces is exactly the same. Right? It's not like I got a different answer. It's the same magnitude. It's just the direction of the force is different to what we assumed at the beginning. Okay? So what's happening is here is this 10 newtons of force pulling up the hill is just enough to prevent the book, this massive physics book, right, falling down or rolling, I don't know, sliding down the hill. Right, so now we have our normal contact force and we have the friction force, right? So at this point, we can calculate what they want, right? They wanted us to find the coefficient of friction. And they also wanted us to find the magnitude of the contact force. So the magnitude of the contact force, the total contact force is both the normal contact force and the friction force together. So let's first work out the coefficient of friction. So if friction is equal to the coefficient of friction between the two surfaces and the normal contact force, well, we were able to calculate our friction. Our friction is 17.3. We can actually just make that 17.4 if we're rounding correctly, newtons. Right, the coefficient of friction is the thing we're trying to work out. And the normal contact force is the one that we worked out as 75.2. Right, I've got this stored in my calculator. There we go. Right, at this point, if you have not kept your original answer, so if you have rounded and deleted your answer from the calculator, it would be a good idea to go back and recalculate that. Right? And the one I have incorrectly calculated was the friction force. It was negative, so I'm going to change mine to a positive value. So that will be and I want to store that as X. There we go. Sorry. Right. So I'm going to recall my Y value and divide that by X value. And I'm going to get 0.23. I'm going to round to 3 significant figures because that's usually what you do, right? And there's my coefficient of friction. Okay, so the coefficient of friction between the book and the surface it's on is 0.231. Okay. Now, Kiana, is that going to change if I apply more tension on the book, if I pull it up at a greater force? Or is the coefficient of friction going to remain the same between these two objects all the
It's going
time?
to remain the same.
Okay, so yes, it's going to remain the same. So regardless of what happens here, how much tension I pull the book up at, this coefficient of friction will always stay the same between the two different surfaces. The only time it will change is if either of the two surfaces change. So something you can think of is either the road surface changes, so it goes from a proper road surface to an ice surface, so the coefficient of friction would change there. Or you take sandpaper. If you use sandpaper, it creates friction, but as you use the sandpaper, it gets less rough, and so the friction becomes less, right? And that's because this coefficient is changing. But if we assume that the frictions are going to remain the same, then the coefficient of friction will remain the same. Right, we also wanted to find the magnitude of these two, right? So the magnitude of the total contact force. And so we can just recall this formula. And hopefully you've again stored these numbers in your calculator, right? So it's a very good idea to start getting used to that now. Because especially when we're working with trigs and stuff like this, just a few decimal places out can give you a different answer to the question. Right, if I take r squared f squared and I square root of that, I'm going to round to 3 significant figures and I'm going to get 77.2 newtons. So that's the total contact force. Right? So the total amount of force generated by the surface. So the surface is not only pushing up with a certain amount of force, it's also creating this friction force. And in our case, this is the magnitude of that force, right? Combined. Cool. Everybody happy, clappy, not so confused?
I'm good.
All good over here.
You good?
Good.
Yeah, Zara, are you sure that that definitely answers your question about the direction now of the friction force?
Yep.
Yeah?
So, Mr. James, the likelihood of us getting a negative answer is the same as making the wrong assumption.
You are making the wrong assumption, okay? It just means the assumption that you've made was wrong, all right? Because actually, if you consider this friction force, all right, we got a force here of F is equal to minus 17.3616, okay? And if we considered that force here, it would be minus 17.3616, right? Look at my direction of acceleration. My direction of acceleration is this way. And we consider forces that act in the opposite direction to be negative. And so actually what you're doing is you're taking the negative of a negative number, which means it had to be positive to begin with. So that's why you're getting a negative number, right? It's because it's in the opposite direction to the direction that you assumed. Okay, part B says find the largest force up the slope for which the book remains at rest. Right, now it's kind of putting the light bulb on and saying, oh, actually we weren't pulling this book with enough tension. We were only holding it with enough tension to prevent it from slipping down the hill. Now we want to find out, right, how much do I actually need to pull this book up the hill, right, to get it to a point that it's just about to move, okay? So this is what we would end up with, right? We're pulling the book up the hill with amount of tension. The friction is now going to work against us, right? It's going to prevent the book from wanting to come up the hill. And we want to find the tension this time. Okay? We still don't know the normal contact force or the friction force, so we're going to have to go and work those out quickly. Okay? I'm going to steal this quickly. So in the same way that we worked out the normal contact force in the last one, if we look at the diagram, the only force that acts against the normal contact force is the vertical component of that 8 newtons, right, which we actually worked out in the previous step. So R was just equal to 8G, right? It is the adjacent side, so cos 20 degrees, right? Exactly the same as the previous one. Right? 8G just being 80, right? The G just being 10. Are the three of you finding it difficult to use 10 and not 9.81? Is the temptation there?
The temptation is there.
You're going to have to write it on your exam paper. G equals 10, exclamation mark. And when you write,
You know
Well,
what?
no, technically we
do
have to
that.
use what they use on the paper, because I saw in one of the past exam papers where they used 9.81 and then another one where they
Okay.
used 10.
This is why I encourage you guys to use this for now, right? And then when you're actually doing the calculation, it forces you to think, oh, what must G be equal to? Okay, instead of just assuming that it's 10. Because like you say, the question might actually tell you, make it 9.8 or 9.81. Okay, this is going to be nice and easy. This is the same as the previous one. So what did we have? 75.2 newtons. Right, that's going to help us now work out our friction force. Okay, because we don't have, remember this object is on the edge of equilibrium, so we don't know the tension. Right? We need to work out the tension. And so in order to calculate the friction, we can't rely, like in the previous one, of saying it's in equilibrium, therefore the friction must be equal in equilibrium to the force being applied on it. However, from the previous question, we worked out the coefficient of the friction force. And because the surfaces haven't changed, we can use that to our advantage. So friction is equal to the coefficient of friction times the normal contact force. And so we can just solve for it. And we can use that 0.231, and we can multiply it by the contact force. And if we round that correctly, we get 17.4 newtons. So this is 0.231 that we got from the previous question. And this is the 75.2 newtons that we reworked out again. So now we have the friction force. Okay? Now we can just resolve horizontally to find the tension. So let's look at all the forces that are acting horizontally. Okay, we have this tension force acting up the hill. We have the friction preventing us from pulling the object up the hill. And then we also have this horizontal component here from the weight of the object that we mustn't forget about. It's easy to forget about this guy here sometimes. He's sort of hanging off on the bottom there. Don't forget about the weight of an object. It's always there. Right, these objects are in equilibrium, which means that the forces acting in the opposite directions must be equal to each other. So the friction is acting in one direction. The horizontal component from the weight is acting in the same direction. And the tension is the thing acting in the opposite direction to them. And from here, we can just find T. So T will just be equal to 17.4 plus, what's it going to be, 80 sine 20. And that works out to 44.7 newtons. Okay, so a dual step problem where we have to use the answer from the previous step in order to find the next step. Okay? So remembering that the coefficient of friction, it will remain the same unless they specify that it changes. Okay, last example. Here we have a container on a rough slope of 18 degrees. So here's my 18-degree slope. Here's the weight of the object acting vertical, right? Because gravity pulls straight down. Here's my normal contact force, which acts perpendicular to the slope, which is why it's not vertical, because the slope is not vertical or horizontal. There is some tension. And what they want us to do is find the range of possible values for T, right? So we want to find the range, meaning what's the least amount of tension that's holding the container there from rolling down the hill, but also what's the maximum amount of tension that I could pull it at that it would just resist moving up the hill. In other words, we're pulling it with just enough power that it's on the verge of going up the hill, right? So the limit of equilibrium. And so we need to consider both scenarios. So the one I've got here is the scenario where I've got just enough tension and the object, you can see the friction force is acting with the tension. So this means that it's preventing it from moving down the hill. We will also have to consider the tension as we're pulling on it and the friction working against us this time. So you can imagine this tension is going to be greater than this tension. Here we've got just enough tension to keep it from rolling. The other one is enough tension to prevent it or to get it to a point where it just wants to move up the hill. So we need to find the tension, right? And just like in the previous step, we need to know what the friction is. We've been given the coefficient of friction this time, so we don't have to go and work it out. So we need to find R. R is just going to be made up of the vertical component of that 400 newtons or the 400 kilograms. By now, you should have worked out that the vertical component is usually going to be the adjacent side, so cos of the angle of the hill. Start learning to spot patterns. And if we want to resolve the friction or for the tension force, we can see the tension and the friction force are acting in the same direction. So we need to find the friction force. To find friction, we will use the coefficient of friction and friction, okay, and the resistance force that, or the contact force that you just calculated. So if you want to be clever, you can just say it's going to be 0.3 times 400 G cos 18 degrees. Okay. At the end of the day, we want to calculate the tension, hopefully in one step, without having to recall functions on our calculator. Right, now we just need to solve for T, and we need to just resolve in the direction of motion. So the only force acting against the direction of motion is going to be this horizontal component from the weight. That's going to be the opposite side from my 18 degrees, so it will be sine 18. And it's all by itself. The tension and the friction are both acting in the opposite direction. The tension is what I'm trying to work out. And the friction we will add, and that's going to be 0.3400 G cos 18 degrees. Okay. And so in one step on my calculator, you can see I can calculate the tension. In one go, right? That's an alternative to writing the answers down and rounding. You can keep them in exact form by keeping them as sine and cos for a while. And then you can resolve in one step on your calculator. You can punch all that information in and you can get the tension, right? And you can round it to 3 significant figures, 94.8 newtons. Everybody still with me there?
Yes.
Yep.
Okay, now the next part of the problem, I'm actually just going to move this up. Let's move him into the view now. The only difference here is now the friction force is acting in the same direction as the horizontal component from the weight. In other words, this part here is just going in that direction now. And we could go and recalculate everything if we wanted to. But we could just do that in one step, right? So we don't have to go and work out the normal contact force again because it's the same. We don't need to work out the friction force because it's the same. Right? The contact force hasn't changed and the coefficient of friction hasn't changed, so everything has remained the same. Right? The only difference here is the direction that the force is now acting in. Right? It's acting in the same direction as this horizontal component from the weight. And the tension this time is the one sitting all by its lonely self on the other side there. And again, in one step, because we've kept it as sine and cos, we can just punch all of that one go into our calculator without worrying that we've forgotten something. And we can calculate the tension as 2,380. This is rounded to 3 significant figures, by the way. That's why we have that 0 on the end. And so if we want to find the range of values, well, the range of values are those are the range of t. So between those range of values, the object would remain stationary. There wouldn't be enough tension. There would be enough tension to prevent it from rolling down the hill, but there would also not be enough tension to actually pull it up the hill.